Okay, the first problem we'll look at in 15.4 is number 2. We have z is 9x squared plus y squared plus 6x minus 3y plus 5, and p0, the point, is at 1, 2, 18. Okay, so the tangent plane, let's start. Let me just check this. F of xy, um, f at 1, 2 is going to be 9 plus 4 plus 6 minus 6 plus 5, and that's 18. Okay, and the partial with respect to x is going to be 18x. Y is a constant, so anything with y is going to be 0, plus 6, and f of y is going to be 2y minus 3. Now, evaluated at the point 1, 2, that's going to be 24, and this evaluated at the point 1, 2, y is 2, so that's going to be 4 minus 3 is 1. So remember, z, the plane, tangent plane, equation is f of ab plus f of x ab times x minus a plus f of y ab y minus b. So this is going to be 18, that's f of 1, 2, plus f of x evaluated at the points 24, x is 1, this is 1, we evaluated that, and this can be y minus 2, b is 2. So tangent plane equation is 18 plus 24x minus 24 plus y minus 2. And we have z equals 24x plus y minus 8. That's the equation of the tangent plane. Now, let me look and do this in Maple. Let me open Maple up. It's always better to work in the classic. Okay, the first thing I want to do for this problem is define the function. So also I'm going to graph it. So let me open this up. I'm going to say with plots, I need that package. And let me make this big. Okay. I'm going to define z to be actually this function. So it's a function of x and y. And you use the same thing as how you define a function with one variable. And we're going to define that as 9 times x. Don't forget your times. I always do that and it messes up if you don't put your times in there. Y squared plus 6 times x minus 3 times y plus 5. Okay, so there's my function. P1, I'm going to define it to be a three-dimensional plot of z. And let me say x is negative 10, 10. We might have to adjust the domain and range. Oh, I go up here. We don't really want the output for that. P2 is going to be the plane, and that's 24 times x plus y minus 8. And I want to suppress that. And then I want to display P1 and P2. And there I have it. You can see let's box it. As you turn around, you can see kind of how it just touches it. Touches this at the point 1, 2, 18. So that's a pretty good picture. Okay, so there's the tangent plane and the surface. Now I want to show you how you can find the partials. Let's say dx, let's define that to be the different derivative of z with respect to x. That should give us the first partial. And then if we want to plug in, evaluate it, we can evaluate it at, we'll plug in 1. X was 1 here. And it gives us 24, which is what we got by doing it by hand. And then we can take the first partial with respect to y. And we'll evaluate it. Again, that's the same thing we got. And this time y is 2. Now we got 1. So that checks. All that checks. So we can do partials with Maple, and then we can plug the numbers in that we need. So that's how we can graph the surface and the tangent plane to the surface. Okay. All right. Let's go to number 12. Here we have, this is, forgot to put the number, 12. F of xy here is x over y, and the point is 6, 3. So f with respect to x, that means y is constant. So the constant just comes out in front. 1 over y is the constant, and derivative of x is 1. F of y, x is constant. So we're just going to do x times the derivative of 1 over y, which is x minus x over y squared. Now evaluated at the point f of 6, 3, f is just going to be 2. 6 divided by 3 is 2. And evaluate this at 6, 3. That's going to be 1/3 y is 3. And evaluate this at 6, 3. And that's going to be minus 6 over 9, which is negative 2/3. So the equation of our, well, we'll get to the equation first. F of x and f of y exist for y not equal to 0, and we have the point 63, so y is not 0 here, so they exist. So I'm going to use the theorem. We're going to exist near 6, 3. That's good. And then we have to show that they're continuous. Well, they're continuous at 6, 3. They're just not continuous for y equals 0. So that's the only thing we have to worry about. So it satisfies those two conditions. That means our function is differentiable. And the linearization of it, the tangent plane, is going to be f of 6, 3 plus 1/3 x minus 6 minus 2/3 y minus 3. That's going to be 2 plus 1/3 x minus 2 minus 2/3 y plus 2. So that's going to be 1/3 x minus 2/3 y plus 2. That's also the equation of the tangent line near the point 6, 3. Let's look at 18. Here's the function. The point is 7, 2. The partial with respect to x, the function goes on the bottom. You take the derivative of the function with respect to x. Y is a constant, so derivative of x is 1. With respect to y, x is a constant, so the derivative of this is 0. The derivative of negative 3y is negative 3. So evaluated at 7, 2 is going to be 1 over 7 minus 6 is 1. And this one evaluated at 7, 2 is minus 3 over 1. 7 minus 6 is 1, is negative 3. And f of 7, 2 is ln of 7 minus 6 is 1, which is 0. So the linearization is 0. That's the f evaluated at the point, plus 1 times x minus 7 minus 3 y minus 2. So L is x minus 3y minus 7 plus 6 is minus 1. So I want to approximate f of 6.9 and 2.06. Again, notice that's close to 7.2. So approximately, if we use the linear approximation, that's going to be 6.9 minus 3 times 2.06 minus 1. I'm using this equation right here, and that's going to be negative 0.28. So that's the approximate value of f at that point. If I want the actual value, I'm going to substitute this back into the f equation, which is ln of 6.9 minus 3 times 2.06, and that's negative 0.3285. So that's the actual, and notice we are very close with our approximation. Okay, in 22 we're going to use a table. T is around negative 15 and V is around 50. So I know from the table that f of negative 15, 50 is negative 29. Okay, first thing you do. Then I can do f of t, the first partial with respect to t, is limit h goes to 0, f of negative 15 plus h, 50, minus f of negative 15, 50, over h. If h is plus 5, then this part right here is going to be negative 22 minus 29 over 5, and that's going to be 1.4. If h is a negative 5, we're going on either side. Using your table, you can see that that's going to be negative 35 minus 29, so it's plus over negative 5, and that's going to be 1.2. So their average we'll take is 1.3. So we're going to use that for f of t. And f of v is the limit of h goes to 0 of f of negative 15, 50 plus h minus f of negative 15, 50 all over h. This time we have to use tens because the table goes by tens. So that makes this 60. F of negative 15, 60 is negative 30. And this is a minus 29 over 10. So that's going to be negative 0.1. And if I use negative 10, that's going to be f of negative 15, 40. That's going to be negative 0.2. So f of v, the average of those two, is negative 0.15. So the linearization is f of negative 1550 plus f of t, which we said was 1.3, t plus minus a minus 15, so it's plus. This is f of t, t minus a minus 15, plus f of v, which is negative 0.15. v minus 50. So that's going to be negative 29 plus 1.3t plus 15 minus 0.15 v minus 50. If I want f of negative 1755, I'm going to say that's approximately equal to the tangent plane at that point. So if I plug that in here I get a negative 2. I get a 5 here. If I use my calculator, that's negative 32.35. So that's going to be approximate function value by using the tangent plane to the curve at the point around negative 1550. Okay, let's look at 24. The differential of that is fx dx plus fy dy. Vx, the derivative with respect to x. Y is a constant, so that's just going to stay there. The derivative of cosine is minus sine. Y is a constant, the derivative of x is 1, so that's going to be times y again. Then Vy, we have to use the product rule. It's the first times the derivative of the second. This time x is a constant, so we can take the derivative of y, it's 1, so I need an x. I'm taking the derivative of the inside, plus the second times the derivative of y, which is 1. So dv is going to be minus y squared sine xy dx plus cosine xy minus xy sine xy dy. And that's it. Okay, 32, I'm just going to say the height is 80, doesn't matter. The width is 60, the length is 50. All of these are off by 0.2. We want the maximum error, so we use a positive 0.2 for maximum error. Let me just draw this box. Call this the height, the length, the width. If I want the surface area, I have two of these, so 2 times h times L, two rectangles. I have two of these sides, and those dimensions are height and width. And then I have two top and bottom, so that's 2 times the width times the length. So dA is going to be A with respect to h times dh, but that's going to be 0.2. That's our error. It's going to be A with respect to L times the error L. It's also 0.2 because that's what it told us. And the area with respect to width times 0.2. The area in the width is error in the width is 0.2. So when I take the derivative with respect to h, it's going to be 2L plus 2W. Everything else is a constant. With respect to L, it's 2H plus 2W. With respect to W, it's 2H plus 2L. And if I substitute in 80 for L, so it's going to be 160 plus 60 for W. Height is 80. $60. L is 50. Sorry, this is 100. L is 50. And if you add all those up, you get 152 centimeters squared. So that's going to be your difference in your area if you measure just 0.2 wrong in each direction. So you get a pretty big error if you do that. Okay, hope this helps.